All right, so we'll take a look, and what we're going to do today is I'm going to just do a couple examples of principal components analysis here. Okay, and so for this, I'm going to load in some heptathlon data. Okay, and let's go ahead and take that. I think this is from the 1980 something Olympics. Okay. And heptathlon, this is a women's heptathlon, and the kind of the heptathlon record holder is Jackie Joyner-Kersee from the U.S. And anyway, they compete in 7 events: hurdles, high jump, shot put, 200-meter run, long jump, javelin, and 800-meter run. And the Olympics have some kind of scoring system for how the events should be scored. So they have these numbers, and basically, if you run the 100-meter hurdles in 13.85 seconds, you score 1,000 points. If you take 16 seconds to run them, you get 700 points. If you jump 1.82 meters, you'll get 1,000 points in the high jump. If you only jump 1.57 meters, you'll get 700 points in the high jump. Okay, and anyway, so we can see, these different people. They had different kind of performances, and this is kind of their final score. And so, what we want to do is we're going to do principal components analysis, and we're going to take the 7 columns, and we are going to try to see if we can reduce the 7 columns down to 1 column, 1 principal component. And we'll just see kind of how that 1 principal component compares to the original score here. Okay. So one thing that we're going to do first is we're going to so most of these things, so out of the 7 events, 4 of them, like the high jump, the shot put, the long jump, and the javelin, higher numbers indicate better performance, right? Higher numbers means you jumped higher, or you threw the shot put or the javelin farther, or you jumped farther, right? Other things like the hurdles, the 200-meter and 800-meter run, lower numbers are better because those are timed events. And so lower numbers mean you ran faster. And so what we're going to do is we're going to take, for each of these, we're going to take the slowest hurdle run, the slowest 200-meter run, and the slowest 800-meter run. And we're going to subtract off everybody's run times. Okay, so this will effectively reverse the order so that in all of these, higher numbers will be better. Okay, and then we'll also pull out the score column and remove that kind of from our data set. All right. So so here is kind of a plot of all the 7 events, and they're kind of their correlations with each other. They're kind of, these are all the different biplots that are not biplots, 7 scatter plots that you can get. And if we just take a closer look, that's because 7 by 7 is a lot. If we take a closer look, what we notice is that there's this one person who had very low high jump, very low hurdle scores and stuff. And so so there's a kind of a poor performing outlier, all right, and that's whoever this person was, Launa from Papua New Guinea. And we can see this person's score is just kind of much lower than everybody else's. And so I think for the sake of our analysis, it might make sense to kind of remove the outlier. So we'll go ahead and do that. Okay. And if we plot that, with the outlier removed, now we can see kind of all the dots here. And some of these things have high correlation, like the 200-meter run and the long jump. Very high correlation there, okay? Other things don't have as much correlation, like the javelin throw and the 800-meter run, not as much correlation. So that's something interesting to note. The long jump and the hurdles have high correlation, but other things that you might not have expected, like the 200-meter run and the shot put, actually have a fair amount of correlation. Shot put and long jump also have a fair amount of correlation, which you feel like, oh, well, I don't know anything about track and field, but you feel like those are different things, but there's a fair amount of correlation there. So what we're going to do is we are going to drop the score column, okay, so that we just have kind of the 7 columns of events. And then we're going to do our principal components analysis, okay? And so the principal components analysis for us will be, we're going to center the data. So we're going to find the means of each column, and we want to subtract the means from each column. So I'm going to do the column means of heptathlon. So here's heptathlon is the 7 columns of data. And what I'm going to do is I'm going to calculate the mean of each of those columns, right? And so if I show you what that is, these are the means of each of the 7 columns. And what I want to do is I want to subtract each mean from the column. Now, R, when you tell R to subtract a vector from a matrix, what it's going to do is it's going to apply that vector down the column. So it's going to take this first value and subtract it from this first value. And then it's going to take the second value and it's going to subtract it from this one. And what we want it to do is we want to subtract it from this one. And we want the third value to subtract from here. But by default, R always goes down the column first. So to get it to work, what I'm going to do is I'm going to transpose the matrix. Okay, I'm going to transpose the matrix, and then I'm going to subtract down the column, which will work. And then, so I transpose the matrix, they subtract the means down the columns, and then I transpose it back. Okay, and so I can do that. And so now, so this will work now. Okay, so we've subtracted everything off. So everything now has a mean of 0, and so if I ask for the column means of my center data, we can see that the column means is pretty much 0 for all of these values, right? Where you get 10 to the negative 17, 10 to the negative 16, just artifacts of the, what do you call it? Floating point system that we're not getting truly 0, but things on the order of 10 to the negative 17. Okay, so that's our centered data, okay? And now I'm going to find the covariance matrix of our centered data, okay? So, so we have a 7 by 7 covariance matrix. And now I'm going to take the eigenvalues and eigenvectors of our covariance matrix. And I do this by calling eigen on the covariance matrix. So I say eigen on the heptathlon covariance matrix. And the results of eigen, you get 2 parts. You get a list which has vector values. So we get the 7 eigenvalues, and then we get the eigenvector matrix, which consists of the 7 eigenvectors, each column being the eigenvector. Okay. And so if I want to reduce this down to one principal component, I'm going to just keep the first eigenvalue and eigenvector, right? So I'm going to just keep this first eigenvector, and these 7 weights are how we should project the data. So to project the data, I'm going to take my, I think I've got 24 competitors in 7 columns, and I'm going to multiply it by just this first column, right? So I'm going to just keep the first column of the matrix, which is 7 rows, 1 column, and I'm going to take my centered, my data here, which if I ask for this, the dimensions of this is 24 by 7. I'm going to multiply that by my 7 by 1, and that's going to reduce it down to 1 column, right? So this is it. If I ask for the dimensions of this, this is going to be 24 by 1. Okay, and this is these are the results here. Okay, and if I compare the results of what we want to see is we want to see very high correlation, and we do have pretty decent correlation between the projected data and the original scores, but the correlation's a little bit off, okay? And it's not quite as good as we might want, okay? And part of the reason for that is that in the original data, okay, the difference between, say, a poor high jump performance and a good high jump performance is very little, right? Like if you look at the scoring system, the difference between like 800 points and 1,000 points is, you know, the difference, you know, like 0.16, right? It's a very small number, okay? Whereas if you're looking at something like the 800 meters, the difference between 800 points and 1,000 points is closer to like 15 seconds. Like it's a bigger number, right? So we have a lot of variance here and very little variance in this column. And so the variance in this column overshadows everything else, okay? And so because this person, Bamer from, I think, East Germany at the time, really did well on the 800-meter run, that person's principal component score ends up being much lower than probably it should be, okay? And then this person, Yu Ping from China, who had a fairly poor 800-meter run performance, their principal component score is a lot higher, or you know, it's not as good as it should have been, okay? Because the variance in the 800-meter run is kind of overshadowing everything. So what we want to do is we are going to, instead of looking at the covariance matrix of the center data, we will look at the correlation matrix of the center data, okay? So the correlation matrix, what that basically does is it scales everything into, so everything has means of 0, but also variances of 1, and then we can do that. So here I'm going to find the eigenvalues, eigenvectors of the correlation matrix, okay? And then again, we're going to just keep the first column, and then we'll go ahead and project it down, okay? And so if I do this, we get a lot better correlation between the results, right? So when we use the covariance matrix, this is what we had. And when we look at the correlation matrix, this is what we get. So we get a lot better correlation here, okay? And so this is what we have. And so now, kind of our top 3 finishers are the same top 3. These are the 3 lowest numbers. So Joyner Kersey has the highest score. These 2, silver and bronze, are in different orders here, okay? But we're recovering a lot of the original information. So this is a good thing. This is something that we want, okay? And yeah, that's what we get. Now, if you do principal components analysis in R, you're probably going to use this function called prcomp, okay? And so here, I'm going to do principal components on the heptathlon data, which doesn't have the score column, okay? And so the result of principal components, scale equals true means we're going to do the correlation matrix, okay? And this is the results of the principal components, okay? And what you'll see is that if I look at kind of the first principal components loading that I got from the correlation matrix, we can see that the values that we got by doing kind of the eigenvalues and eigenvectors ourselves are the exact same values that prcomp returns for us, okay? So our numbers are exactly the same, and this is kind of the result of the prcomp from R. One thing that you can get when you do principal components analysis, okay, it will kind of tell you the, it'll give you the proportion, the cumulative proportion of variance. So if you only keep the first principal component, you'll capture around 60%, 62% of the original variance. And if you keep two of them, you'll get about 75% of the original variance. And you can also create something called a biplot, okay? And so, you know, when you do kind of your gold medal finish final rankings of the athletes, you're only looking at basically one dimension, right? You're going from best to worst, okay? But if you look at the values, you know, as far as the principal component scores that we get, there's a lot of people kind of in this middle range that have very, very similar scores to each other. They're all around -1 and between -1 and +1. And it's kind of difficult to tell the difference between all of these things, right? These two people, Greiner and Libernova, their scores are almost the same, and it's the same up to 3 decimal points. How do we differentiate these, right? So we can take a look at the second principal component, and what we see in this plot, okay, is we see so in the first principal component, all the arrows are pointing in the same direction, okay, and but in the second principal component, we see high jump pointing in one direction, going down, and run 800 pointing in the other direction. And basically what this is saying is that, you know, look at this, these two people, Yuping and Brown, they basically score, they're very far on this side, okay? Very far on this side means their high jump was either very high or their 800-meter run was very low, okay? And indeed, if you look at the original data for heptathlon, Yuping from China, her 800-meter run was very poor comparatively, right? Versus Brown from USA, also this person's 800-meter run also quite low. Okay, the numbers here are very low. Versus you know, something like Joyner Kersey and Bämer from Germany, very high performance for the 800-meter run. Okay, and you know, if you look at the high jump performance of Yuping and Brown, we also see, you know, their high jump performance is very high, 1.86, tying with Joyner Kersey, our kind of our gold medal finisher here for the high jump, 1.83. You know, again, very, very, very high. Versus, say, Jeremias from Brazil, their high jump performance not as great. Okay, and then also on the biplot, if you look, so here it would be Chobankova right here, either indicating low high jump performance or good 800-meter run performance. And if you look at Chobankova, you can see, oh yeah, the 800-meter run performance was very high, and the high jump performance, relatively low. Okay, so that's kind of an interesting thing, and basically it's saying if you needed to kind of a second dimension to differentiate, one from another, you can look at because these arrows are pointing in different directions. That's kind of a way to kind of indicate that. So that is that's principal components analysis in R. There's a few more things, and I'll post up these this code here as far as doing principal components analysis, and in your homework, your next homework assignment, I'm going to have you guys do some principal components analysis here. I wanted to do something. This is completely unnecessary, but I thought it was kind of a neat use of principal components analysis. And what I'm going to do is I'm going to load up this this image of Audrey Hepburn from the movie Breakfast at Tiffany's. So this is kind of an old classic movie. Maybe you're familiar, maybe you're not. This is an iconic scene from the movie Breakfast at Tiffany's, and the idea that I want to show here is that we can apply principal components analysis for dimension reduction on an image. Because if you think of an image, what an image is it's really just a matrix. It's a matrix of, in this case, this is a 791 by 634 pixel image. I've got 791 rows and 634 columns of values. Okay, and the way it's represented here, if we just kind of take a look at say like the first 10 rows and the first 10 columns. Okay, maybe I should just do like the first 8 columns. We just have a whole bunch of numbers here. Okay, and this would be kind of like the top left corner here. And this top left corner is mostly black, and so we got values that are close to 0. Okay, if I go to another part of the image that is fairly bright, say this looks to be maybe around, I don't know, 180 pixels in and 400 pixels. So for the row, so if I go to like row 400 to 410, and as far as the column, we go to like 180 to 8 or something. Okay, so in this part of the image, we get values that are close to 1, because this part of the image is very bright white, so we get values that are close to 1. So, as far as this image goes, values close to 0 would be something close to black. Some values close to 1 would be pixels that are white. And so this whole image is just a giant matrix of 791 rows, 634 columns. Okay, and what we can do is we can take this matrix and we can reduce the number. What I want to do is, right now you can think of it as having 634 variables. What I want to do is I want to reduce that down to, say, 50 variables. Okay, and so so we're going to reduce the do principal components analysis to do some dimension reduction here. Okay, so so the first thing is to center my data by taking the column means. Okay, and then I'm going to subtract the column means from each column, right? So I transpose it, subtract the means, and then transpose it back. And we can verify that are all the column means equal to 0, and it is. And let me just show you what the image looks like after I've subtracted the column means. So after I subtract the column means, I get these vertical streaks in here. And the idea here is that basically if you look at the average of the entire column, you're going to get the same value of 0, which or relatively speaking would be kind of like gray, okay? And so that's what we get here, okay? And so what we see is, image in a column where there's lots of white, it kind of grays it out here, and then in a column here where there, if you look at it, her arm happens, she is wearing a black glove, and her arm, it happens to be kind of vertical here or something, and so there's kind of this a lot of black pixels in this one column here, and so you kind of get this streak where overall it kind of brightens that proportion just so that the average ends up being gray there as well, okay? So anyway, I've centered the image and kind of puts in these vertical streaks because everything, we want the mean of the column to be gray, okay? And now we'll go ahead and do our eigenvectors, okay? So, sorry, I'm going to find the covariance matrix, okay? So the covariance matrix of this thing, because our image has 634 columns in it, 634 columns of pixels, the covariance matrix will be 634 by 634. Then I can find the eigenvectors, eigenvalues and eigenvectors of this covariance matrix, okay? Whoops. And if I check the structure of that, we're going to have 634 eigenvalues, and I'm also going to get 634 eigenvectors, each eigenvector being of length 634, right? So here I'm doing kind of the eigenvalues and eigenvectors of our covariance matrix. And then the last, what I'm going to do now is we're going to do, let's say we want to just keep 50 of these principal components. So I'm going to just keep kind of 50 columns out of the eigenvectors, okay? And so we'll do that. And so these will be the weights, okay? Right? We got I'm going from 634. M is 634, and I'm reducing it down to D being 50. And so I've got 50 vectors, each of length 634. And so these are going to be the weights that I use to reduce my dimensions. And so to get my lower dimensional data, I take the original matrix, Audrey centered, which the original data, this is 791 rows by 634 columns, right? 791 by 634. And we're going to multiply it by PC50, which is 634 by 50, right? So the result of this, when I do that, when I project it down, is going to be 791 by 50, okay? So I've reduced my image from 791 rows and 634 columns down to 791 rows and 50 columns, okay? Now, if I try to display this, right? If I try to show you what this image looks like, okay? This image will not look like anything, okay? 791 rows, 50 columns, this doesn't look like anything. This is just like a gray rectangle with some blotches here and there, okay? This is a rotation of the image, okay? A rotation of the data, I should say, rotation of the data in the image that is, the original data exists in 634 dimensions. We got 634 columns in, and we're reducing it down to kind of a 50 dimensional piece of information, right? And so this is that projection. And this is, it doesn't look like anything if you try to graph it like this. But this image actually, or this data actually captures a lot of the variance in the original data, right? So if we want to reconstruct the original image, I have to take, so what I've done is I've reduced it from 791 and 634 down to 791 by 50. And what I want to do is I want to reconstruct the original image. So I can multiply it back by the transpose of the kind of the weights that I've used. Right? So if I do that, the recovered image, the dimensions of the recovered image is going to be 791 by 634. Okay, and so what I can do is now that I've recovered it, I can add the means back, and I can plot this. Okay, and so this is the image that I get after recovering it, after I project it back from 50 columns back to 634 columns. Okay, let me compare that to the original image. Okay, so this is the original image, and I hope what's being broadcast, you can tell the difference. So the original image is very sharp, very clear, and this is the image that we have recovered after reducing the original data down to kind of 50 columns of data. So I reduced it from 791 by 634 down to 791 by 50. Okay, and basically the idea is you don't have to, like, this is a lot of values, right? 791 times 634, that's 500,000 values, right? 502,000 values, right? And 791 by 50, that's only about 40,000 values, okay? So you can transport, like if you needed to send this over the internet or something in a compressed form, you can send this a lot fewer values, like 1/10 of the values, and give it the instructions on how to recover the image, and you can get this back, okay? Whereas the original image looks like this, right? So you're not getting as much of, you're losing some image quality, but you can still definitely tell what the picture should look like, right? So this is the original data, and this is the data after we've kind of compressed it from 634 columns of data down to 50 columns of data. All right. Now, so at a theoretic level, you can use principal components as a form of kind of image compression. You could, right? You could take the original data, 791 by 634, and you could compress it down to an image like this, where you only kept, like, say 50 of the columns of data, right? So it is possible to recover the image like this and use it as a form of image compression. But at a practical level, this is not what image compression, what the internet uses. The internet uses JPEGs today. JPEG is another what we call a lossy image compression format, and it uses something called wavelets, and it doesn't work using principal components. Theoretically, you could do it, but kind of from an engineering standpoint, the computation involved in finding the eigenvectors, compressing it down, and then undoing that dimension reduction is computationally expensive, so it's less desirable. Also, in the transport, if something gets messed up, say in the image, the instructions on how to go from 50 columns back to 634, if those instructions get messed up, then the image will not be recoverable. So so things can go wrong, and so it's not the method of choice used for image compression. But from a theoretic standpoint, it could be done. Okay. I wrote a loop here that goes through and just shows you what the image would look like if, instead of keeping 50 principal components, what would happen if we only kept one, or what would happen if we kept 2 or 3 or 10 or 12 or something like that. And I tried a various number of principal components, and I just kind of want to show you the results of that. Okay, so this image is actually the same image. So this is the original image, and this is what we get if we keep only one principal component. Okay. So if you keep only one principal component, this is what we get. Okay. And so this looks nothing like the original image. But you do see that, you know, here's kind of this patch of very bright white, and that kind of is reflected here. But other than that, this thing looks very not like it, right? If you keep two principal components, this is the structure that you get. And so now we're starting to see a couple regions, right? Here's kind of this bright white area from the it's probably like a window or door that's open, letting some like light from outside in. There's also these bright white napkins, and we get a little bit of that structure here. With the third principal component, we get a little bit more of the structure that exists in the original image. Here it is with four principal components. With four principal components, we're starting to see a little bit of this up and down shape of the napkins, and we see also the structure of the lights here and the door that also appears right there and right there. And so here it is with five principal components, and then at six principal components, now you start to see right here, this looks like where her eyes and eyebrows are. Okay, her eyes and eyebrows are right here, and we're starting to see that appear in the image as well. Okay, and so at 10, now we see something that resembles a face. Okay, again, doesn't quite you know, it's, if you squint and you you know, you take off your glasses and you go, oh yeah, that there is some similarity between this image and this image, but you know, it's you know, at 10 principal components, there is some similarity, but it obviously not a very good one, right? But it's impressive that, you know, the original data had 634 columns, and here we're basically keeping only 10 of those columns, and we're still able to get a lot of the quote structure that exists in the original image, right? And so as I include more principal components, the image becomes more and more clear. So at 20 principal components, I would say these two images are starting to look fairly, you know, this definitely resembles this image, even though this is very grainy, very blurry, and not doing a great job. Here it is with 25, and here it is with 30 principal components. And I'd say at 30 principal components, we're doing a fairly good job. And then here's, you know, 50 principal components, which I showed you earlier as kind of our first example. And as I go up and add more and more principal components, the image just becomes more and more well-defined, better clarity, and more contrast, okay? It's interesting, even this part here that includes kind of the copyright notice, that actually appears in our image, right? When we recover more and more principal components, that aspect of the copyright notice actually shows up in the corner there. Okay, so here it is with you know, 250 principal components and things like that. We get quite a bit, and the difference between 250, 300, 400, and 500 principal components is hardly noticeable. As far as the difference in the image quality, I would say even between 180 principal components and the original, it's difficult to tell the difference. Which is impressive to say that, you know, the original image, we needed all 634 columns of pixels, and what we can do is, you know, we can transport something with a lot fewer columns and still recover something that looks like the original image. So, you know, from a theoretic standpoint, principal components analysis for dimension reduction can be used in a situation like image compression. It's not though, but it is neat that we can apply this, and we can see that when you reduce the number of dimensions, you can still recover the original structure fairly well, right? So the idea again is, you know, if I give you just the shadow of a three-dimensional object, and you take that shadow and you basically just print a 3D version of the shadow, okay, you've lost that third dimension, but you know, you'll still get an object that looks like the original thing. You'll still get an object that looks kind of like a hand, even if you don't have even if it's not fully realized as such. All right, that's all I have for you guys today. So we'll end here. Next week, lectures are optional, and we'll just kind of take it easy. I'll probably do like one topic of interest, and then you know, kind of like extended office hours. I'll answer any questions you guys have and things like that. So we'll end here, and have a good weekend. Oh, the quiz answers for today. It's 9th week Friday. Quiz answers are A and D. A as in apple, and D as in dog. So we'll do that. I'm sorry, I'm not going to post homework solutions. Unfortunately, it only takes one student to mess things up, and you know, students have dishonored my request to not share even just like class notes. So I'm not going to post homework solutions. Okay. What topic am I thinking about? I don't know. I haven't decided. I was thinking maybe like decision trees and random forest, but I don't know. Something topic of choice. Do you have a preference? Midterm grades will be up by the end of the week. So basically I'm going to give myself today and tomorrow to get everything there. But that's what we've got going on. Yeah, there's a lot of overlap in 101C. I don't. Do you have a request if you don't want decision trees? So I think a lot of people haven't done 101C yet. The complement. You want the complement of 101C? Everything that's not covered in 101C. All right, I'll think about something. I'll think of something to talk about. Okay. Next homework assignment will cover PCA. Okay. And that's it. So, all right. Maybe we'll see you guys next week. Maybe not. So have a good weekend, and see you Monday, maybe. Oh, I missed it.